This is the last section, 8.6, rolling motion. A rolling motion means that there's no slipping point at the point of contact with the ground. So if the tangential velocity is velocity linear, it's the point at the outer edge relative to the circle. So in figure 8.15, an automobile moves with a linear speed v. If the tires roll and do not slip, the distance d through which an axle moves equals the arc length s along the outer edge of a tire. So that I wrote below, distance d equals circular arc length s. So I also wrote that we're going to be dealing with the same thing with tangential velocity equals radius times angular velocity, and tangential acceleration equals radius times angular acceleration, which is all in linear. So let's check our understandings with a concept question. If the speedometer of a truck is set to read the linear speed of the truck, but uses a device that actually measures the angular speed of the rolling tires that come with the truck, however, the owner replaces the tire with a larger diameter version, does the reading on the speedometer after the replacement give the speed that is A, less than, B, equal to, or C, greater than the true linear speed of the truck? So the answer is A, less than. Why? It's the reason why it's A is because linear equals tangential velocity equals radius times angular velocity. So when the speedometer measures the same W as before, the velocity is greater because the tire's radius is larger than before. So if you're ever in doubt about knowing whether or not it's equal to, less than, or greater than, just plug in numbers to prove your point, and so you can find the ratio between them two to be able to find what your answer is. Now let's look at question 53. A motorcycle accelerates uniformly from rest and reaches a linear speed of 22 meters per second in a time of 9 seconds. The radius of each tire is 0.28 meters. What is the magnitude of the angular acceleration of each tire? So we already know our tangential velocity, which is the linear speed of 22 meters per second. We know our time, which is 9 seconds, and we know our radius, which is 0.280 meters. And we know that our tangential is also our final because we know that our initial is 0 because it told us that it started from rest. Okay, so if we know the acceleration is final velocity minus final initial over time, then we know 22 minus 0 over 9 because 22 is the final, the initial, you get me, and then it would give us 2.44 meters per second squared. So we already have the angular, no, forgive me, we already have the tangential acceleration. So we can use the formula tangential acceleration equals radius times angular acceleration in order to find our angular acceleration. So you would use tangential acceleration over radius. So we already have our tangential acceleration, which is 2.44, and you would divide it by the radian given, so it's 0.28 meters, to be able to get the angular acceleration of 8.71 radians per second squared. Okay, let's look at 54. An automobile tire has a radius of 0.330 meters, and its center moves forward with a linear speed of v equals 15 meters per second. A. Determine the angular speed of the wheel. B. Relative to the axle, what is the tangential speed of the point located 0.175 meters from the axle? So we write the givens down. The radius is 0.330 meters, and it's moving with a linear speed of v equals 15.0 meters per second. So that's our tangential velocity. So it's asking us for our angular. So we can use the formula that I used before, which is tangential velocity equals radius times angular velocity. So you would divide the radian by each to be able to find the angular velocity equals tangential velocity over radius. So it's the velocity of the car over radius. So it's 15 over 0.33, which would give you the angular velocity of 45.5 radians per second. Okay. Now they're asking us for the tangential speed of the point located 0.175 meters from the axle. So we know that there's a new radius, which is 0.175, and we can still use the same formula, tangential velocity equals r times angular velocity. So we would just multiply each. So we would have the 0.175 from the new radius, and we would multiply it by the angular speed, which is 45.5, in order to get the tangential velocity of 7.96 meters per second. A lot of chapter 8 is a repetition of what we learned before. It's just a changing in variables or finding new things. So you had already known that this, oh, this is not a pretty, okay. We already know that the centripetal acceleration was velocity squared over radius, so you're just introduced to it in a different way. So now it's radius times w squared. Or kinematics, the same thing. You guys now know that acceleration now looks like this, and now velocity now looks like this, and x now looks like this, but time is always the same. And just overall, you know that it's just changing in variables to know different things. So you already knew based on what you guys learned from the angular kinematics or rotational kinematics, and in order to go back to linear, you would have to multiply it by its angular version, and you would have to also multiply it by the radius. And that's basically it. If you have any trouble with concept questions, like I was saying before, you would just plug in numbers, try to find the ratios, and you would just have to remember what you remember from linear kinematics and try to apply it to rotational kinematics.